December 16, 1811, 2:15 in the morning. In the frontier settlement of New Madrid, the night suddenly began to roar. The sound came first. Witnesses compared it to distant thunder, except deeper, rougher, and somehow beneath them. Then the ground moved, not as a single jolt, but in long, rolling waves. Trees cracked, riverbanks collapsed, sand and water burst through fissures in the earth. On the Mississippi, waves surged upstream so violently that people believed the river itself had reversed direction. More than 1,000 miles away, historical reports say church bells rang from the shaking. This did not happen in California. It happened in the center of the North American continent, far from any tectonic plate boundary, beneath a region where roughly 11 to 12 million people now live along the wider strait. Lewis to Memphis corridor. And today, more than 2 centuries later, scientists still disagree about what New Madrid is doing. The United States Geological Survey maintains that the region remains a serious earthquake hazard, but Northwestern University seismologist Seth Stein argues that nearly 20 years of precise GPS measurements reveal almost none of the ground motion normally expected where strain is accumulating for another major earthquake. His conclusion is provocative. The great earthquakes at New Madrid may be part of an episode that is now ending. So is New Madrid reloading for another disaster, or is America preparing for a fault system that is slowly switching off? To understand that argument, remember 3 dates: 900, 1450, 1811. Those dates were not preserved in books. They were written underground in buried columns of sand. By the end of this story, you will understand why no scientist can safely fill in the 4th date, and why that blank space may be more dangerous than any prediction. When Americans think about earthquakes, they usually think about California. There, the San Andreas Fault marks the boundary between the Pacific Plate and the North American Plate. The plates move past each other continuously. Strain accumulates. Instruments can measure motion in millimeters and in some locations centimeters per year. New Madrid has no nearby plate boundary. The New Madrid seismic zone stretches from northeastern Arkansas through southeastern Missouri and western Tennessee and Kentucky towards southern Illinois. It lies deep inside the North American Plate, thousands of kilometers from the plate's active edges. In a simple version of plate tectonics, this part of the continent should be quiet. But continents are not unbroken slabs. They contain ancient scars, failed rifts, buried faults, and zones of weakness left behind by geological events hundreds of millions of years ago. Stress transmitted across a plate can sometimes reactivate those weaknesses. The result is an intraplate earthquake, an earthquake occurring within a tectonic plate rather than along its boundary. These events are rare, but they can be devastating. Charleston, South Carolina was struck by a major intraplate earthquake in 1886. Bhuj, India, suffered another in 2001. New Madrid is the best-known North American example because of what happened during one winter, between December 1811 and February 1812. The same physics, a very different address. At 2:15 on the morning of December 16, 1811, 31-year-old Eliza Bryan was in New Madrid. She lived with her mother, who operated a boarding house in the settlement. Eliza would later provide one of the most important surviving eyewitness accounts of the disaster, an account preserved by the Center for Earthquake Research and Information at the University of Memphis. She described a terrifying noise, the violent movement of the ground, and air darkened by what she believed was sulfurous vapor. Around her, residents ran outside without knowing where safety could be found. Animals cried out. Trees fell. The Mississippi River roared in the darkness. Modern USGS estimates place that first main shock at approximately magnitude 7.5, although no seismographs existed in 1811, so every magnitude assigned to the sequence is a reconstruction based on damage, felt reports, and later geological evidence. Within minutes, the ground opened. Water-saturated sand beneath the surface lost its strength under intense shaking. Pressure forced sand and water upward through cracks, creating eruptions known as sand blows. Some covered fields. Others formed long dikes below the surface across the region. Liquefaction features eventually affected an area of roughly 10,400 square kilometers. A.N. Dillard was a child when the earthquakes occurred. In an account published decades later, he recalled that his father lost a shipment of metal castings when the ground swallowed it. The British naturalist John Bradbury, traveling on the Mississippi during the first earthquake, described collapsing banks and a landscape descending into chaos. The first main shock was not the end, it was the beginning. USGS records indicate that 6 powerful aftershocks, estimated between magnitude 5.5 and 6.3, followed during the first 2 days. Shaking continued through the winter. On January 23, 1812, a second major earthquake struck, now estimated at approximately magnitude 7.3. Then came February 7th. At about 3:45 in the morning, the largest or one of the largest earthquakes in the sequence ruptured near New Madrid. Modern estimates place it near magnitude 7.5, although some published reconstructions place it higher. This time, the river became the center of the story. The earthquake deformed the riverbed and surrounding land. Sections of ground rose while others subsided. Large waves moved upstream. Boats were thrown into confusion as the water surface tilted, surged, and changed direction. To people trapped in the darkness, it appeared that the Mississippi had begun to flow backward. That description has survived for more than 2 centuries, but the scientific explanation is more precise. The entire river did not simply reverse its normal current for hours. Local uplift, riverbed deformation, and powerful seismic waves created temporary upstream surges and the appearance of reversed flow. The correction does not make the event less terrifying. It makes the mechanism more extraordinary. Near what is now northwestern Tennessee, land subsided by several feet, while deformation disrupted existing drainage. Water flooded the lowered terrain and helped create Reelfoot Lake. A landscape that had been forest and swamp was transformed into a permanent body of water, leaving dead tree trunks standing above the new surface. The scale of the shaking was enormous. USGS estimates indicate that motion strong enough to alarm the general population covered approximately 2.5 million square kilometers. Damaging shaking affected about 600,000 square kilometers. Chimneys fell as far away as Cincinnati and St. Louis. The earthquakes were reported across much of the eastern United States and into parts of Canada. The exact death toll will probably never be known. The settlement was small, the region was sparsely populated, and deaths on the river were poorly recorded. USGS documentation identifies only one confirmed death caused by a falling building in New Madrid, while historical accounts describe additional drownings and losses that cannot be counted with confidence. That uncertainty matters. A low recorded death toll does not mean the earthquakes were mild. It means the earthquake struck a frontier with very few people and very little infrastructure. The population of Missouri at the time was only about 20,000. Today, the wider St. Louis to Memphis region contains roughly 11 to 12 million people. The seismic zone does not run directly beneath every one of them, but a repeat of the 1811 and 1812 sequence could affect communities across several states. The disaster also produced an overlooked political aftermath. In 1815, Congress approved what is often described as the first federal disaster relief act in United States history, providing land certificates to people whose property had been destroyed. But speculators quickly bought some of those claims from desperate survivors for a fraction of their potential value. Even after the ground stopped moving, the disaster continued in a different form. If you want more investigations into disasters that transformed America and then disappeared from public memory, subscribe now. Because the next piece of evidence was not found in a letter or a ruined town. It was found 2 meters underground. The problem facing modern scientists was simple to state and extremely difficult to solve. Were the earthquakes of 1811 and 1812 an isolated catastrophe, Or were they the latest sequence in a repeating pattern? There were no detailed written records for the centuries before New Madrid became an American settlement, but an earthquake powerful enough to liquefy the ground leaves evidence that can survive much longer than a building, a diary, or a human memory. That evidence is buried sand. During liquefaction, sand is injected upward through overlying soil. After the earthquake, new sediment gradually covers the deposit. Organic material above and below it can then be dated using radiocarbon techniques. By comparing sand blows across many locations, researchers can determine whether they were probably produced by the same earthquake sequence. This is where Marticia Tuttle enters the story. Known to colleagues as Tish, Tuttle and her collaborators examined hundreds of earthquake-induced liquefaction features at more than 250 sites across the New Madrid region. The work extended across Missouri, Arkansas, Tennessee, Kentucky, and Illinois. Each trench exposed layers of soil that functioned like pages in a damaged archive. The method required extreme care. Radiocarbon dates have ranges of uncertainty. A sand blow at one site might be associated with an earthquake recorded at another site dozens of kilometers away, but only if the dates, structure, size, and distribution matched. One incorrect association could create an earthquake that never happened or divide a single sequence into several false events. The pattern that emerged was difficult to dismiss. Tuttle and her co-authors identified major earthquake sequences around the year 900, with an uncertainty of roughly 100 years, and around 1450, with an uncertainty of roughly 150 years. Their liquefaction features were similar in scale and distribution to those produced in 1811 and 1812, 900, 1450, 1811. The broader geological record also contains evidence of older large earthquakes, including possible events around the year 300 and approximately 2350 BC. But the three recent sequences provide the clearest pattern for the current debate. In their 2002 study, Tuttle and her colleagues calculated that the intervals between the three recent sequences could have been as short as about 200 years or as long as about 800 years, once dating uncertainties were included. The average was roughly 500 years. That average is important. It is also dangerous if misunderstood. An average recurrence interval is not a schedule. The ground does not wait 500 years. Check a calendar and rupture. Three recent sequences are not enough to establish a precise cycle. Even the dates of the prehistoric events contain uncertainty measured in decades or centuries. The last major sequence ended in 1812, approximately 214 years ago. In the 2002 paper, Tuttle's team noted that if the shortest inferred interval was used, the region had already entered a period in which another comparable sequence could occur. That was not a prediction. It was a statement about possibility. And this distinction between a possible event and a predictable event sits at the center of the New Madrid controversy. To understand the consequences, look beneath Memphis. The New Madrid system is associated with the Reelfoot Rift, an ancient zone of weakness created during a failed attempt to pull the continent apart hundreds of millions of years ago. The rifting stopped, but the damaged crust remained. That ancient structure was later buried beneath much younger sediment in the Mississippi embayment. According to the USGS, marine sedimentary rocks in the embayment are roughly 50 to 100 million years old, while river sediments are generally younger than 5 million years. The upper 30 meters include sand, silt, and clay, deposited largely during the past 60,000 years. Those soft, water-rich sediments matter because they can amplify particular frequencies of seismic shaking. They are also vulnerable to liquefaction. The same ground that supports roads, pipelines, bridges, warehouses, schools, and homes can temporarily lose strength when shaken hard enough. There's another difference between eastern and western earthquakes. The crust beneath the central and eastern United States is generally older and more continuous than the heavily fractured crust of the tectonically active West. Seismic energy can therefore travel farther with less attenuation. A New Madrid earthquake may produce severe local damage near the rupture, but its shaking can also be felt across an unusually large area. In 2009, a FEMA-funded study led by the Mid-America Earthquake Center modeled a catastrophic magnitude 7.7 New Madrid scenario. The model assumed rupture across all three principal fault segments and examined consequences across 8 states. This was not a forecast of what will happen. It was a deliberately severe planning scenario designed to expose vulnerabilities. The results were staggering. Nearly 86,000 casualties, including approximately 3,500 deaths. About 715,000 damaged buildings. More than 7 million people displaced, with roughly 2 million seeking temporary shelter, approximately 2.6 million households without electricity, and more than 1 million without water, thousands of damaged bridges, with around 15 major bridges rendered unusable. Direct economic losses approaching $300 billion before the full effect of national supply chain disruption was counted. Now translate those statistics into time. Imagine the scenario beginning at 2:15 in the morning, the same hour as the first Great Shock in 1811. This is an illustration based on the planning model, not a prediction of the exact sequence. In the first seconds, seismic waves spread outward from the rupture. Communities closest to the fault receive little or no useful warning. People wake to violent motion before they understand what is happening. Furniture crosses rooms, masonry cracks, power lines swing. In areas vulnerable to liquefaction, pavement deforms as water and sand force their way upward. Within the first minute, emergency calls begin arriving from several states at once. Some older brick facades fall into streets. Automatic alarms activate in hospitals, factories, schools, and warehouses. Electrical faults trigger scattered fires, but damaged roads and broken water lines make them harder to fight. Within 5 minutes, the earthquake is already a transportation crisis. Bridges must be closed for inspection, even where no damage is immediately visible. Freight trains stop. River traffic loses reliable communication. Drivers encounter fractured pavement, fallen overpasses, and traffic signals without power. Within the first hour, aftershocks complicate every rescue. A building that survived the main shock may fail during the next strong tremor. Hospitals attempt to move patients while evaluating damage to their own structures. Emergency managers request information from counties that cannot respond. Millions of people reach for mobile phones at the same time, overloading networks that may already have lost power. By sunrise, the scale of the event is still unknown. No single camera can show it. The affected region is too large. What appears to be one earthquake on a national map has become thousands of separate emergencies, connected by broken roads, interrupted utilities, and the same river system. Those figures describe a model, not a certainty. The real numbers would depend on the exact fault segment, magnitude, time of day, season, river level, building occupancy, and success of emergency response. But every major version of the scenario points toward the same structural weakness. The region contains a large inventory of older buildings and infrastructure never designed for intense earthquake shaking. Unreinforced masonry is especially dangerous. Brick walls can appear solid for a century and then separate from floors and roofs within seconds. Historic commercial blocks, churches, schools, fire stations, and older residential buildings are among the structures that can be most vulnerable. Transportation would become a second disaster. Interstates 40 and 55 cross the wider region. Major bridges connect communities and supply chains across the Mississippi and Ohio rivers. If river crossings, rail lines, ports, pipelines, and highways failed at the same time, emergency crews would not simply face damaged buildings. They would face damaged buildings they could not reach. Utilities would compound the crisis. The planning model estimated more than 1 million households without water and millions without electricity. Hospitals could be damaged at the same moment that demand for emergency care exploded. Communications could fail while state and federal agencies attempted to coordinate across an 8-state impact area. In 2011, the United States government tested that problem through National Level Exercise 2011. More than 10,000 participants from federal, state, local, international, private, and non-governmental organizations took part in a full-scale exercise centered on a catastrophic New Madrid earthquake. The exercise did not prove that the model would unfold exactly as predicted. It revealed how difficult the response would be, even when everyone knew the earthquake was only an exercise. For perspective, the 1994 Northridge earthquake in Southern California had a magnitude of 6.7, lasted only seconds, killed 57 people, and caused tens of billions of dollars in losses. Southern California had earthquake-aware engineers, trained emergency services, and building codes shaped by previous disasters. The New Madrid scenario is larger, spreads across more states, and strikes communities where earthquake risk competes for attention with floods, tornadoes, ice storms, and hurricanes. Before we examine the scientist who believes this danger may be overstated, tell me in the comments whether you live anywhere between St. Louis and Memphis or elsewhere in the central Mississippi Valley. Then stay to the end, because the scientific dispute does not produce one winner. It produces a more unsettling answer. In the late 1990s and early 2000s, Northwestern University seismologist Seth Stein and his colleagues began testing one of the central assumptions behind the New Madrid hazard model. If major earthquakes repeat every few centuries, where is the strain accumulating for the next one? At plate boundaries such as California, GPS stations detect the slow relative movement of the crust. Some fault sections remain locked while the surrounding ground deforms. That measurable motion provides evidence that elastic strain is building. Across New Madrid, however, nearly 20 years of high-precision GPS observations failed to reveal comparable motion. Depending on the analysis and location, estimated deformation was extremely small, roughly at or below the millimeter per year scale and sometimes statistically indistinguishable from zero. For Stein, that absence is not a minor detail. It challenges the idea of a fault reloading steadily toward another magnitude 7 earthquake on a simple 500-year cycle. His alternative model is that intraplate earthquakes are episodic, migrating, and clustered. A fault system inside a continent may become active for a limited geological period, produce a cluster of major earthquakes, and then quiet down as stress migrates elsewhere. Under that model, the sequences around 900, 1450, and 1811 might represent an episode approaching its end, rather than a permanent cycle continuing indefinitely. Stein developed this argument in his 2010 book, Disaster Deferred: A New View of Earthquake Hazards in the New Madrid Seismic Zone. His position does not mean earthquakes have stopped. Small earthquakes continue. It means the next major rupture might be much farther away than recurrence calculations suggest, and that public resources should be allocated according to risk rather than fear. This is a serious scientific argument, not denial. But it is not the only interpretation of the evidence. The USGS and other researchers point out that New Madrid is not a plate boundary system. Its deformation may be distributed over a broad area, occur at depths or rates difficult to resolve, or vary through time. A short GPS record may not capture the behavior of a system whose earthquakes are separated by centuries. There is also the geological record. Whatever the GPS stations detect today, large earthquake sequences did occur around 900, 1450, and 1811. Sandblows cannot explain exactly what the fault is doing now, but they prove what it has done before. In 2006, the USGS convened experts to review earthquake hazards in the central and eastern United States. The group examined the lack of measurable surface deformation and concluded that the GPS evidence was not strong enough to justify reducing the official New Madrid hazard assessment. A later independent expert panel also concluded that the zone continued to present significant risk. Then there is the question of the small earthquakes still occurring beneath the region. Approximately 200 small earthquakes are recorded in and around the New Madrid zone during a typical year, most too weak to be felt. But scientists disagree about what those earthquakes mean. A study publicized by the USGS in 2014 concluded that modern seismicity did not behave like a conventional aftershock sequence from 1811 and 1812 and instead indicated continuing stress. A study published in 2023 reached a different result, estimating that as much as 65% of the seismicity between 1980 and 2016 could be long-lived aftershocks of the large 19th century earthquakes. If many of today's earthquakes are aftershocks, that supports the idea that intraplate faults can remain disturbed for centuries, but it does not, by itself, prove that the system is harmless or that a future large earthquake is impossible. This is why the argument survives. The GPS record asks a powerful question: where is the measurable strain? The geological record answers with another: if the system produced several major sequences in the recent past, what evidence is strong enough to justify ignoring it? The USGS currently estimates a 25 to 40% probability of a magnitude 6 or greater earthquake in the New Madrid region within the next 50 years. It estimates roughly a 7 to 10% probability of a sequence comparable to 1811 and 1812 during the same period. Those numbers are probabilities generated from models and assumptions. They are not countdown clocks. 7% does not mean safe. 40% does not mean inevitable, and neither number identifies a year, a month, or a day. People sometimes compare these percentages directly with California, but such comparisons can mislead. Different forecasts use different magnitude thresholds, geographic regions, time windows, and fault models. The important contrast is not a single percentage, it is preparedness. California has spent decades strengthening bridges, hospitals, schools, and critical infrastructure. The central United States has improved planning and adopted modern codes in many places, but large inventories of vulnerable older structures remain. That creates the New Madrid paradox. The probability of an extreme earthquake may be lower than in the most active parts of California, but if it happens, the consequences could spread across a much larger region that has less recent experience with destructive earthquakes. So who is right, Seth Stein or the United States Geological Survey? The evidence does not support a simple victory for either side. Stein is right about one crucial point: the 500-year average must not be treated as a schedule. The lack of plate boundary style GPS deformation is real, and any model of New Madrid must explain it. The USGS is also right about one crucial point: the absence of a clear GPS signal does not erase the geological record, eliminate uncertainty, or make vulnerable buildings stronger. Hazard policy must consider both probability and consequence. That is the answer hidden inside the debate. New Madrid is not proven to be overdue. It is not proven to be dead. It is a low-frequency, high-consequence system whose behavior scientists still do not fully understand. 900, 1450, 1811, 3 sequences preserved beneath the Mississippi Valley, 3 warnings written in sand, waiting centuries for Marticia Tuttle and other researchers to read them. The average interval between the recent sequences was about 500 years, but the possible intervals were much wider. The last sequence ended 214 years ago. GPS instruments now watch the surface with extraordinary precision, yet the 4th date remains blank. That blank does not mean tomorrow. It does not mean 500 years from now. It means we do not know. And uncertainty is not the opposite of danger. In disaster planning, uncertainty is part of the danger. Geology does not follow election cycles, construction budgets, or human attention spans. It does not care where one state ends and another begins. It does not care whether the people above it believe an earthquake belongs in California. The New Madrid story is not a prediction of apocalypse. It is a test of whether a society can prepare for a disaster that may not happen in our lifetime, but would be catastrophic if it did. If you want more evidence-based investigations into the forces building beneath America, subscribe and turn on notifications. The first 3 dates are already written. The 4th is still blank.